We are the Integrated Bionic Microsystems Laboratory, our iBionicS lab at the Department of Electrical and Computer Engineering. We work at the intersection of electronics and biology, with bioelectronic applications starting from wearable devices for humans to dogs, all the way to plant health monitoring. In this video, we highlight some of our work aimed towards improving quality of human life. One of the things we are trying to investigate is how we can predict asthma exacerbation due to exposure to environmental parameters. Here you can see a lab-based data collection in progress. The app here shows data being collected from a wristwatch and a chest patch. The wristwatch gives us ambient ozone level data. We also get wrist motion data seen here as a set of 3 state lines for a resting hand. We also get PPG or photoplethysmography for retrieving heart rate data from the wrist watch as well as the chest patch. PPG, as can be found in many smartwatches, is an optical technique which measures blood volume changes from which we can obtain heart rate data. The chest patch also gives us ECG or electrocardiography. Our goal would be device data correlation through advanced data analytics such that events like asthma exacerbation can be predicted in advance. A wearer can perhaps take medications, suspend current activity, or get indoors to possibly prevent that onset.
We are also building wearable, wireless electrochemical platforms to continuously sense concentrations of biomarkers in bodily fluids. These types of systems will one day give physicians and caretakers new metrics to monitor the health and wellness of their patients. In the iBionicS lab, we designed the software and hardware systems for these devices, which we then combined with novel electrochemical systems designed by our collaborators. Another project in our lab utilizes a technique called functional near-infrared spectroscopy, or FNERs, to monitor oxygenation in tissue. By applying these systems to the head, we can actually monitor localized oxygenation in the brain, which is related to localized brain activation. We're designing a fully wireless, miniaturized wearable FNER system, which will allow researchers to monitor brain oxygenation and activation in real-world environments, leading to a deeper understanding of how the brain functions in the real world. But these systems can be applied in fields from basic research to neurology to psychology and psychiatry.
In the picture here, the smart textiles are integrated into a shirt. They're able to detect things like perspiration, pulse rate, small electrical signals that are coming from the body, and pressure. These textiles can be used in far more ways than just shirts though. The first of these are printed pressure sensors that can be used in prosthetics. And the goal of these sensors are to be a comfortable way to gather more information on where those pain-causing pressure points are and make it a faster and easier process to reach that final version. A similar approach was also taken to create an insole pressure sensor to analyze gait. When you're walking, the pressure distribution of your foot changes, and the sensor allows that to be monitored to detect any irregularities that may cause issues down the road. The final example to show is this smart glove. Here, the pressure sensors on the back of the hand can be used as a way to control other devices wirelessly. There are countless ways this technology can be used to help people, from simple convenience to improving welfare, and I'm very much looking forward to seeing those possibilities. It's been an incredible experience that's given me the opportunity to be exposed to new technologies, get hands-on experience, and learn how many of the fundamentals that are taught in class are actually used in the engineering process. I would wholeheartedly recommend it to anyone remotely interested in research, even if you are not planning to go into graduate school, although it does help smooth that transition over as well.